we discuss more about dual slope ATD converters using microcontrollers, how to do ATD conversion using microcontrollers. In the previous lecture we had seen simple RC circuit, we had a RC circuit and then V input was given here, and then this was exponentially rising with the time, and then basically time versus voltage, that to reach particular voltage how much time it takes, that was measured using a microcontroller. This type of converter is very simple to use, but nevertheless this is not accurate like what we had discussed earlier, the dual slope converter. The converter can be improved by using a constant current source, which we already discussed. So, what can be done is constant current source based ATD converter we can use. ADC. So, here what we can do is we can have a current source, constant current source, which actually we already discussed in our earlier lectures. So, we can have a, for example, we have the input voltage given here, which is to be measured V input, and then we will have the current flowing through this, and that can be allowed to charge a capacitor. So, this is R, and then we will call this is R sense resistance, and then these are all fixed values of R. Then current through this is given by V in by Rs, is the current that is actually going through this. And if I have a capacitor C, then the capacitor C linearly charges with the time. So, if we take this, the capacitor C charges linearly with the time. That means, if you look at the capacitor voltage, that if you write the basic equation CV is equal to I into T, then the voltage on the capacitor is given by I into T by C. That actually V in by I we can be replaced by V in by Rs, and then T by C. So, obviously that is the voltage at this point, that is V is actually proportional to V in, that is for example, there are two ways of utilizing this. If this is V input voltage, suppose this is the voltage that is to be measured. If V in is the voltage to be measured, if V in is the voltage to be measured, then we can write V in terms of V in, we can write that will be V into Rs into C divided by T. So, V in actually proportional to if this is constant, if I fix particular V, for example, if I fix a particular V, so which I can do in a simpler way. What I can do is that I can have this capacitor which is constant charging through a constant current source, and that is a V in which is powering the constant current source. I can give this one to a comparator in the microcontroller. This can be a reference to V. So, as soon as the charges up to V, then goes up, then the state change occurs at the output of the comparator. The state change can be measured by measuring the time t. For example, what can be done is, in actual case we can have a discharge mechanism from microcontroller, and this can also be fed to a microcontroller. So, it can discharge first the capacitor. So, discharge the capacitor C first, then allow it to charge. As soon as reaches the voltage V, the state change occurs here, and that microcontroller can sense and then find the time between discharge to the state change at the comparator. So, essentially the steps involved are first discharge C, C, then after discharge, after discharge, start the timer. The second step is wait for comparator rollover. Once comparator changes state, that happens at V reference, okay, V reference, then wait for comparator, then measure, then stop the timer. So, the time gives you V in, the time t gives you the V in using this formula one can find, because all these parameters are fixed. So, one can do this. In this case, that nonlinearity problem is not there, because current source charging linearly, whereas earlier we had a problem of RC converter which was actually charging exponentially. So, the circuit works much better. Still the dual slope problem is not dual slope conversion is not achieved even in this. Now, even this can be done in a different way. For example, even I can do you can do in other way of doing is would be that you can have a constant current source, which we had shown you here, that same constant current source you can have. Then I can give here V reference, so that the current goes and charge at a fixed rate. Then this can be compared with the reference. This can compared with the V reference, V input, so that the output state change can be sensed. And of course, similarly we have to have the discharge mechanism for this. This and this can be given to microcontroller. This can also be given to microcontroller. This is V input. So, in the similar to the above method, first we can discharge the capacitor C and then start the timer. Then as soon as the comparator rolls over, then you can stop the timer, and the time can be measured here. Now, the same equation applies here also. So, here only thing is that if I have a constant current source I, that that same this thing that is equal to V in, and then V in actually will be equal to I t by C, and I is constant because we had fixed with respect to V reference. So, the V in is proportional to T. So, here V in is proportional to T. So, this is the advantage in this case. So, the time is not going inversely like earlier system. So, both method can be adopted. Probably this method is better option, because here V in is proportional to time. Of course, for very small voltages, if when you are sitting at very close to 0 level, then T comes very small, and then the measurement gives a problem. Whereas the earlier method that is not a serious issue actually, because here when V in is small, and then you will find T has to be large. Of course, this also introduces problem, but nevertheless most of the people use this kind of system, that is V in proportional T method can be used. So, in this method start the first discharge C and start the timer. Then after that the second step would be wait for rollover, wait for comparator rollover. Stop the timer and stop the timer. So, the time can be measured, and that gives you V in. But if you see both the methods, both of them are not really matching with the dual slope comparator we had discussed earlier. So, how to improve, because the drawback here is suppose the chi changes with the temperature, and then even the change in the resistance with temperature, all will give error, because if C changes, then we see that the C is a parameter in the equation. So, we are just measuring T. So, if you are measuring only T, then we have to make sure that this I and C is constant, but both I as well as C can change with respect to temperature. So, how to modify this for a dual slope converter? Now, one possibility would be have a circuit which has have a constant current source, have a that is I say dual slope converter, dual slope converter with the microcontroller. So, here what can be done is that we can have the current source, the regular current source, here we can have a probably similar to what we had in the dual slope converter. We can have two possibilities, either it can make contact here or here. So, one can given V input, another can be given minus V reference. For example, if you are measuring a plus voltage, then one can give for example, this is position 1 and it is a position 2 for the switch, this is a pole for the switch. So, here is that capacitor that is connected here. The basic idea is, for example, if I have this is R sense and then these resistance are equal, basically I is actually given by if it is connected to V reference, the V input. So, V in by R s, or I minus, this is we call I plus, and I minus the reverse current actually is given by V reference by R s. So, we have when it is connected to V input, it is plus. So, current is flowing like this and charging the capacitor C, and if I switch over to V reference, then the current is reverse and then the capacitor is getting discharged. So, it is similar to the dual slope converter which we had discussed earlier. Now, I will use this converter for measure the V input, the ATD conversion. Now, once you do this, what is really happening is that you will, for example, we can also have a discharge if you want start sometime, the initial thing to be started. I can also have a microcontroller pulse to discharge the capacitor. Once capacitor is discharged and this can be put off this, then once you connect to V in, it will reach allow the V in to charge the capacitor C for certain amount of time. So, what can be done is that I can discharge the capacitor first. So, first step would be discharge C using the switch, S1 I call it, that is S1. So, that can be given from a microcontroller, a pulse can be given here, and that can discharge briefly the capacitor C. Then after that, allow, second step would be allow that I name this one as S2. Allow the switch S2 to connect to V in. So, by doing this we are actually charging the capacitor. So, allow this charge. So, this keep the switch S2, keep the switch S2 for a fixed time t. This can be done easily by a microcontroller, because we can have a switch here, and then this can be connected to another terminal of microcontroller. For example, we can connect P1.0, another port pin we can connect P1.2. So, this can be a MOS switch. So, the on resistance is very small. So, allow this for a fixed time t. Then the fourth option is fourth step would be, after this time t it would have charged for certain voltage, Now, that it would have reached a voltage V, because we know it reached a voltage V equal to, because same equation IT is equal to CV we can use here, that would be IT divided by C, where I is given by V in by RS into C into T. So, since the time t is fixed here, time t is fixed, and it will reach certain amount of voltage V depending upon the voltage V in, that is input voltage V in. If the input voltage is more, then you would have got more voltage in the given time. Then the fourth step would be now keep the switch S2, keep the switch S2 that is change the switch, now change the switch S2 to minus V reference. This discharges the this discharges the capacitor C. How much time it takes to discharge? Time required to discharge would be, time required to discharge would be because total charge discharge can be computed, actually can be computed. This can be done by equating the total quantum of charge that went in. So, the discharge equation is V reference by RS is the current into T of T discharge time, discharge. So, divided by C gives you the discharge voltage. So, this is the same as I into T is equal to C into V. So, we had this as I, and then T divided by C gives you the discharge voltage. If this voltage had been originally V in by RS into T into C. So, this is on time, it is same as what we had discussed in the earlier equation, that we call this as on time, this on time. Now, in this equation that we will get V reference is fixed, and in both sides RS and C goes off. So, you and then this is fixed. So, V reference into discharge, and C also went off. So, you will get V in into T on. Since this is fixed, and then V in actually is given by V reference into discharge time divided by T on, that gives you V in. So, the discharge time gives you the voltage V in. So, this method is similar to the dual slope ADC, which does not involve the capacitor C or the resistance and so on. Even the current source errors, most of them actually goes off, because the time between charge and discharge is very small, and this converter is free from all the errors. It is similar to the dual slope ADC converter which we had discussed. Only thing is, for counting and other operations we can use microcontroller, and this can be made at very low cost, because most of the converters you will have the most of the instruments will have already V reference, and generating a minus V reference is not a difficult job. One can invert it and then feed it to V reference. Nevertheless, it needs minus V reference that is to be generated. That is the main drawback. So, this is not popularly used, even though this is very accurate. So, this is very accurate. Noise averaging can be controlled, noise averaging can be controlled. This is because we are fixing the time, we are fixing the on time, on time. So, if you select on time in multiples of noise frequency, select the on time when multiples of select the on time in multiples of noise frequency, multiples of noise frequency. In that case, in the sense that if I want to reduce a 50 hertz noise, to remove 50 hertz noise, T on can be in multiples of 20 seconds, 20 millisecond. Which will remove the 50 hertz noise. So, the capacitor, of course, capacitor must be low dielectric absorption capacitor must be used. So, the third requirement is low dielectric absorption, low dielectric absorption capacitor must be used. Capacitor must be used. This will actually noise averaging is more accurate, and the noise averaging can be done with on time and so on. Of course, this puts extra burden on the designer, because he had to make the constant current source, and then he has to have the two switches, one to discharge and then one to charge, and then of course you also had to have the comparator here, because this comparator have to be compared with respect to reference voltage, that is 0 in this case. So, it will be known exactly when the complete discharge had occurred. Once complete discharge occurs, the state change have to occur, or it can be even given a very few millivolts can be given here. So, that when the voltage goes below that, the state change can occur, the rollover can take place. So, the discharge can be sensed by using a comparator. So, discharge can be checked by the microcontroller using the comparator. So, this is a dual slope A to D converter, which is actually good, because the noise rejection is inherently there, and then the converter by itself is very simple, but the drawback is it is a very slow process. So, if you look at the advantage of these converters, dual slope converter, the main advantage will be good noise rejection, Then the main disadvantage it is very slow. It is very slow because we have to wait in terms of if you want to remove 50 hertz noise, then we have to wait, we have to charge in multiples of 20 millisecond. That means the conversion possible only 5 or 6 conversions possible in 5 to 6 conversions only possible. Per second. So, to get rid of this speed problem, the another converter we can think of, that is actually successive approximation ATD converter. The successive approximation ATD converter we will have very high speed, but noise rejection is very poor. So, we see how the successive approximation converter is working and how that is used in conjunction with the microcontroller. So, we will see first the basic working principle, and then we see of course, there are standalone converters, and then we can also see how to interface with the existing microcontrollers. This one, there are many microcontrollers today which has inbuilt successive approximation ATD converters. So, we see step by step how these successive approximation ATD converters are used in today's design world. So, we see the next. Successive approximation ATD converter. Now, this is the advantage, this is very fast, that is the advantage, and then disadvantage is noise rejection is very poor. It is completely opposite that of dual slope converter that we have discussed so far. Now, in this converter what is done is that we have comparator here. Now, this comparator, one input is essentially allotted to input signal which is to be measured, V input is connected here. Then we have this output is actually connected to what is called successive approximation register, there, and that actually has the it will do many functions which we will discuss now, and then what is done is that it also needs a DTA converter. Actually, we have a DTA converter here, which we discuss a little later, and the DTA converter gives you analog voltage. This is a V analog voltage that is given back to the other input of the comparator. So, DTA converter actually gets its input from successive approximation register. This is successive approximation register. So, what is really done is that you have a system wherein you have ATD converter actually realized using a DTA converter, that is A to D ADC function is realized using a digital to analog converter. Now, the converter works like this, that is, here if we have a, for example, for 8-bit converter, we take an example for say for 8-bit converter, 8-bit converter, what we do is, we first put that 8-bit converter means we will have 8 bits are there. So, we will have MSB here, and then we have a LSB, least significant bit here. So, I assume that we have 8 bits. So, what I do is I will have, so in this case, okay, I take this is a lower 4 bits and this is a higher 4 bits. Now, what you do is you keep first MSP alone, that is least significant bit alone 1, that is to the digital converter I apply MSP alone kept high, MSP is 1 and all the other bits are 0. So, step 1 would be, first step would be keep MSP, that is MSP, that is bit number 7, that is this is 0th bit 1, 2, 3, 4, 5, 6, 7, MSP bit number 7 is high, all the other bits, other bits 0 to 6 are low. So, you keep MSP alone high, and that is a bit number 7 alone high, and all the other bits keep it low. Now, the ATD converter, the DTA converter gives output corresponding to this MSP. For example, if this has a V reference, if the DTA, this is what is given to DTA converter. The DTA converter responds for this by outputting its analog voltage. If the reference voltage for DTA is 1 volt, for example, if the reference voltage is, if the DTA DAC reference V reference equal to 1 volt, then V output of the DAC would be 0.5 volt, because the V output of the DAC would be V0 of DAC actually is given by the digital value divided by in this case actually in this 8-bit converter 2 power n into V reference. So, in this case it is 1 volt and the digital value is actually, for example, it is 128 in this 256 levels. So, you have 256 levels, 128 is the MSP value and reference voltage 1 volt, that comes as 0.5 volt. So, DAC puts a 0.5 volt and the output of the DAC now is become 0.5 volt. So, if this is MSP is 1, then the output here is 0.5 volt. So, the successor approximation starts its operation by outputting MSP alone 1 and all the other bits are to 0. So, if we have MSP alone 1 and then the DTA converter responds by putting 0.5 volt. Now, the comparator response depending upon whether the input is higher or lower. If the input is higher than 0.5, so if the input V in is greater than 0.5 volt, then comparator output is 0. Greater than 0.5 output is 0. Now, the successive approximation register, that is now successive approximation register SAR, since it received a result that telling that the input is higher than 0.5, because only when the input is higher than 0.5 the output will still remain 0, then SAR what it does, it keeps that MSB 1, that is that MSB which you had put as 1, that is retained, and the next trial it starts. Now, SAR starts its next trial, since in the previous, there is no change in the output, there is no change in the comparator output. The MSP is retained as it is, the MSP, that is bit 7 is kept as 1, as it is kept as it is at 1. Then bit 6 is kept 1, and other bits that is 0 to 5 are kept low. So, now bit number 7 and bit number 6 are high. So, now bit 6 and 7 are high. Now, the ADC response, now the DAC response, DAC gives out for bit 7 0.5 volt, bit 6 0.25 volt, that correspond to 0.75 volt, gives out 0.75 volt. This is for bit 7, this is for bit 6. Now, now the comparator changes output, that is goes high if the input is greater than 0.7, if the input is greater than 0.75, it goes low if V in is less than 0.75, volt. If there is that is, if the input voltage is more than 0.75, then there will not be any change in the comparator output. In that case, if this happens, then bit 7 6 are kept as 1, and if this happens, bit 7 is kept as 1, and bit 6 is put back at 0, back to 0. Then the converter goes for the third trial. After this, then third trial. In this case, here 7 6, that is in this case bit number, in this case in this case bit 5 is kept as 1 and bits 0 to 4 are kept 0. The same thing is repeated. Now the converter now the DAC output is will be it's if 7 6 5. So this if this has been 0.5, if this has been kept to 0.25 and this is 0.125 out have been added. So this would 0.75 plus 0.125, that will be 0.875. If 6 had been kept high, then the input will the DAC will respond by putting 0.85. Now the comparator response, comparator goes high if it is lower than 0.875. So like this the trials are made like this 8 trials are made, 8 trials are made. So in each trial the 8 trials are made. So in each trial if the comparator goes up, that bit is put back as 0, otherwise it is kept as 1. At the end of the 8th trial, the converter output is ready. By this method, by this at the end of 8th trial, the converted digital output is ready. So it took only 8 trials to complete the conversion. So it needs only 8 trials to get the conversion completed. Typically one conversion can be done probably in a microsecond time. So if it is 8-bit converter, it needs only 8 microsecond to complete the conversion. For example, if 1 microsecond is required for one conversion, then only 8 microsecond is required. 8 microsecond is only 8 microsecond is required to complete the conversion. So it is that is why it is very fast. So it is very fast. However, there is one catch in this. If the input in this whole process we assume that input is steady, but the condition is that important point, this is valid only if this is valid, that is converted output is valid only if the input voltage is constant. Input voltage is constant during the conversion time. Because this is valid only if the input voltage is constant during the conversion time. This is a very important thing. If the input changes during the conversion time, then converted result is wrong. If the input changes, if the V in changes during T into 8 period, conversion period, then result is wrong. Then the result is wrong. This is an important drawback of this converter, because it starts from MSP and it continued to convert assuming that the input is constant. After first conversion, if the input had changed, then subsequent results are wrong. So, if you want to make this converter workable, then we have to make some arrangement to keep the input constant. So, how to keep the input voltage constant? How to keep the input voltage constant? For this, one can use a sample and hold. So, one can, that is basically latch the voltage, that is latch the V in, that is the thing that is required. This using sample and hold circuit, How that is done? That is, if you have V input, one possibility is I can have a operational amplifier, for example. Then I can have, for example, the follower here. Then I can have the capacitor here, for example. Now, if it is V in, so this will charge to V in. Now, this can be given to the comparator of the converter. This can be given to the comparator of the converter, and this can be given to the DTA converter. The other circuits being same as what we have discussed. So, this is the capacitor C. So, the V input is actually connected to V input. Now, initially what is done is V input is connected to I have a switch here. I can connect the V input. So, normally what is done is if I connect V in, then this charges to V in. Then if I connect this one, if I open it, then I do not want this capacitor to discharge. So, one possibility is we can have a that is, if I open, the capacitor should not discharge, because what I do is before starting the conversion, I will latch the voltage in capacitor and then I will open this and retain this voltage. So, this we can achieve by adding slightly modifying this. That is, what we can do is that we can have a V input voltage, and then we can have the diode, for example. I can have this, can have a switch here, then I can have this capacitor, then I can have the connected to input, or it can be connected to ground. This is connected to V input. switch S1. This is a capacitor. See, this can be given to our converter, which actually gets the input from our DTA converter, for example, which actually gets from SAR here. This is given to a successive approximation register, which actually gives you the this can be given to SAR, and this is DTA converter, and this can be given to analog voltage, can be given to comparator. So, first S1 is connected to V in, then after some time, after small time connect S1 is changed to ground, S1 tend to ground. Now, the voltage, that is the voltage in C remains constant, voltage in C remains constant. Voltage in C remains constant because it cannot discharge, assuming the bias current is negligible, then the voltage in C remains constant. Now, start the trial. Now, start the so first connected for a small time. So, that is a step 1, then step 2, then step 3 is start the successive SAR conversion. Since the input voltage is kept constant, now the conversion takes place smoothly and there is no error at all. So, this arrangement is called sample and hold, So, sample and this way of acquiring the input voltage, input V in to the ADC is called sample and hold, sample and hold amplifier. This is commercially available, the sample and hold amplifiers are commercially available. So, one can use sample and hold amplifiers are commercially available. Commercially available. By using sample and hold, one can achieve correct conversion using a successive approximation ADC. Of course, there is one drawback in this. Now, the conversion time increased. So, the conversion time is total conversion time. This is actually T acquisition plus T conversion. So, there is a T total. Now, this is the drawback of this. Nevertheless, one can do the conversion without even sample and hold, provided we are sure that the input not going to change more than 1 LSB during the conversion or half LSB during the conversion. So, if sample and hold is not used, or we say sample and hold amplifier, we call it is SHA amplifier is not used, then V input change, delta V in change during the conversion should be less than half LSP. It must be less than half LSP, then only then one need not use the sum and hold. Now sometimes the people do this trick that you can have the input voltage is coming, that for example, if I have a V input, if I am dividing this by a resistance, and if I have a very large capacitor here, then this can be given to for example, this has to go to our ADC output, it can be used for ADC output. Then this SCR successor resistor, and then if C is very large, if C is very large, if C is very large, so that delta V in is less than half LSP during the conversion time, that is during the conversion time. Then sum and hold is not required. So, this way one can actually convert very fast. Of course, the as I said, the noise is a dominant factor, that and also it needs a sum and hold amplifier. Nevertheless, because speed is an important criteria in today's world in most of the conversion work, this successor approximation ADC is the most popular ADC, and it is extensively used in the real world. So, we will see how the different microcontrollers have adopted the successor approximation converters and how to use them, and how to shorten there are a few tricks used by the microcontroller manufacturers to utilize this, and also some of them have this sum and hold, some of them do not have sum and hold. We see these issues in the next lecture. Thank you.